Let us consider this mass m that has been attached to a spring. Now, this is the unstretched position of the spring. Let us say we compress the spring by a distance x1. This is the distance x1 by which we compress the spring. In that case, what is going to happen? The spring will exert a rightward force which will be equal to F is equal to K x1. K is called as the spring constant. Sometimes K is also referred to as the stiffness of the spring. So F is equal to Kx1 happens to be the spring force that is applied towards the right hand side. Here the displacement x1 was towards the left hand side and the force happens to be opposite of the displacement. So this happens to be the magnitude of the force. If we want to write down the force with respect to the displacement, then force vector will be negative of k into displacement vector. So k into displacement vector is scalar multiplication of a vector quantity. So force happens to be equal to minus kx. Similarly, here the spring that has been extended by a distance, let's say x2, will experience a force in the direction opposite to the displacement x2, and this will be given as minus k x2, and in magnitude it will be equal to kx2. And since it is opposite in direction with respect to the displacement x2, so x2 happens to be this displacement. So the displacement x2 is towards the right hand side in this particular case, but the force applied is towards the left hand side. The force, restoring force that the spring applies, happens to be towards the left hand side. So in general, we can say that the spring force F is basically equal to minus kx, where x happens to be the displacement. It is worth mentioning at this point in time that spring force happens to be classified as a conservative force. This force is electromagnetic in nature. That means this force is arising because of electromagnetic interaction between the atoms of the metal that constitutes the spring, and this happens to be a conservative force in nature. So work done by any force is defined as integration of F dot dx. So since this is a conservative force, this work done could be written as negative of change in potential energy of the spring. So this is integration of F, which happens to be minus kx dx. Alright, so let us say from x initial to x final, the displacement occurred. So minus of delta u is uf minus ui. This is going to be equal to minus of half k x final square minus half k x initial square. So the negative sign gets cancelled and we can write down uf minus ui happens to be uf minus ui is equal to half k xf square minus half k xi square. So this means we could write down, so this xi and xf are any arbitrary position. So we could write down in general the potential energy expression for the spring to be half k x square, where x happens to be the displacement from the equilibrium position of the spring. So you can say that the potential energy of the spring is half k x square. So it is worth mentioning about the potential energy of the spring. Now if three springs are connected, three or in general n springs are connected in series with each other as shown in the first diagram, then in that case, let us say if I extend this spring by an extension x, then in that case the restoring force is going to be the same across all the three springs, and the extension X will be shared by the three springs as X1, X2 and X3. So X1 plus X2 plus X3 is going to be equal to X. We assume the springs to be massless compared to the mass M. So they have negligible mass compared to the block of mass M. And since they are massless, they will experience the same force throughout, which is the spring force, or you can say the tension force in the wire connecting the springs. So basically this is going to be equal to, like, this extension happened because of a force F. So that same force F will be Kx1. So x1 will be F divided by K1. So x2 is also going to be equal to F divided by K2. And x3 is going to be F divided by K3. This happens to be F divided by K effective. So instead of writing K effective, I'll write Ks, which is the series spring constant. Therefore, I get 1 upon K series is going to be equal to 1 upon K1 plus 1 upon K2 plus 1 upon K3. So this can be generalized, and we can in general say till 1 upon Kn. So this basically is the expression for the combined spring constant for springs in series. So if we were to replace the three springs with one single spring, it would have the spring constant given by 1 upon Ks is equal to 1 upon K1 plus 1 upon K2 plus 1 upon K3. So I'll highlight this particular equation for the students to remember by heart. Yeah, this is the equation. Yeah, so for springs in parallel, it is important to note that both of these diagrams are diagrams that are relevant for springs in parallel, because springs in series are defined as when the force applied on all the springs is the same, the springs are said to be in series. In parallel, when the displacement is the same, the springs are said to be in parallel. So for all the three springs, you can see that if we move the block of mass m towards the right hand side by the displacement x, then the extension of all the three springs is going to be x as well. Here, if we move this block towards the right hand side with displacement x, then the extension of k1, k2, k3 is going to be x, and the compression of k4 and k5 is also going to be x. So all k1, k2, k3, k4 and k5 will try to push this block away, because spring always tries to maintain its own natural length, and the spring, whenever compressed, tries to push away, and whenever extended, tries to pull the block and get back to its own natural length for minimizing the potential energy, which we know is half kx square. So basically, both these diagrams are considered to be springs in parallel. Although these might look to you as if K4 and K5 are in series with K1, K2, K3, it should be noted that all K1, K2, K3, K4 and K5, all of them are in parallel. So here the restoring force will be F, and here the forces of all the springs get added to give the final restoring force. So here we can write F1 plus F2 plus F3 plus F4 plus F5. This is going to be equal to the force F. And what is F1? It is K1 X. X is common over here. So springs in parallel are defined by X being the same. And springs in series are defined by the force. The springs in series are defined by the force being the same. So K1x plus K2x plus K3x plus K4x plus K5x is going to be equal to K effective, that is K parallel into x. So after cancelling out all the x's, we are essentially left with the expression for K parallel, which happens to be K parallel is nothing but K1 plus K2 plus K3 plus K4 plus K5, and which can thus be generalized to n springs. So in general it is equal to Kn. So this is a result that the student can remember by heart. I'll box it up. Yeah, there we go.